So we're going to start and go over some more of the feedback examples, and hopefully all this business about return ratio analysis will be a little bit clearer. One announcement is that I actually will have a class on Friday in the regular time, so there's not going to be a makeup. I managed to kind of move that trip, but I'm going to make a post on Piazza just so people know to actually show up at the regular class time rather than like 5 p.m. TGI, whatever hour. OK. So also another thing, the homework, so we moved them to today. We're going to do the same thing for next homework, just because I don't want to give you like 3 days to do it. And then we'll see whether we just move everything to Monday schedule, because there will be some stuff at the end where we won't be able to do that. But for now, we're just going to move the homework. Next homework will be released today and due next Monday in class. OK. So we're going to start now with some more feedback examples. So continue sort of the return ratio analysis approach. OK. We did some MOSFET examples, and so we're going to do a bipolar example. Sometimes a little bit more interesting because of this feed-forward resistance, R pi. So I'm going to draw a simplified example where I'm not showing the biasing network, essentially. But normally, there will be some kind of biasing network over here that you would have. But those, we said, those are going to be pretty large resistors anyway, so we can ignore them. OK, so this is the circuit. So it's an emitter-degenerated common emitter configuration. And so we're going to draw a small signal model of this. We have R pi, our emitter. I'm going to have RC here. And the VO will be here. So then just the same way we did it. So the approach I showed you so far was to determine RR first. Then after that, can look for A0. And then look for A equivalent. And then A closed loop will be A equivalent over 1 plus RR plus A0 over 1 plus RR. Right, so that's the recipe, 1, 2, 3, 4. Okay. So the way we do, number one, we do the return ratio. We have to break the feedback loop and then insert the source and then terminate the other side with the impedance that independent source is seeing. Now, in the book, there is a little bit of a difference between that and what I just said, in a sense that they say, OK, well, you have to locate the dependent or controlled source, in which case that would be this, and then replace that with an independent source, and then also monitor kind of the variable that controls this one. That will be a return ratio, right? Difficulty with that is that sometimes it's kind of, that's not the best place to cut the loop. And your analysis can get a little bit more involved if you always follow just that recipe. But really, there's no reason to just go and replace that dependent current, the dependent source, simply because return ratio is a unitless quantity. Wherever you cut the loop, you can essentially terminate and introduce a source. And so you should really be able to pick just a convenient place to do that. OK. So if we go and draw how this circuit here is going to look when we calculate the return ratio. We're going to ground the input. So we have R pi. And then we can cut the loop right here simply because this is VBE. And this is sort of our feedback voltage that we're feeding back, right? So we can cut the loop right there and add VTest. And then whatever we're seeing here, that will be R pi, we're going to terminate with that. And then have RE. And then we're going to measure the return right on that termination. So the return ratio will then be, well, let's first calculate VR, and then we're going to. So VR will be GM times VBE. VBE is minus VT. Times, and then here we're going to have R pi in parallel with RE. All right, so return ratio, by definition, was minus VR over VT. And that's just GM times R pi in parallel with RE. And 2. Oh, let me just climb it up a little bit. 2. If we look at this diagram over here, 2 basically says we're looking for A0, which is how the signal goes from input to output in the case where K equals 0, or K is sort of our dependent source in the circuit. So in this case, what is K? Does anybody know? K was this parameter that was kind of like if there was an amplifier with V error, then the output was KV error, right? Or in that case, K was just A, right? But in the single transistor case, what is K? GM, that's right. So in this case, that means that GM equals 0. So we're looking still at V out over Vn for K equals 0. So we're looking for the feed-forward path that does not involve the transistor. Right. So if K equals 0, that means there's 0 current flowing here through this source, regardless of what VBE is. Right. So what is V out then? If there's no current flowing here, what is V out? 0, right? So then this forward gain is 0. So we don't have it in our, and so in this equation here, this would go to 0, right? Okay? And then what we're left with is this equivalent gain. And for the equivalent gain, we said we're going to calculate it from 3 terms. The first term would be input signal to the controlling signal. That means for output signal being 0. So we're going to draw the whole network. So we're going first through R pi. But then if we take a look at this situation here, if the output signal is 0, that means there is no current here. And looking from this side over here, that's like open. Okay? That means that what I'm seeing from the input is R pi in series with RE. Okay. So the fact that this piece is floating here is because VO is 0. Remember, we had these three terms. The first term was for the output being 0. The second term was for the input being for the gain, and the third term for the input being 0, what really gets transferred from the source, controlled source, to the output. Okay? And then here we have our normal GM VBE. VBE is, of course, here. Then we have RC. And then we have to add the network that we see when Vin is 0. So when Vin is 0, if this node is 0, what do we see from here? Right. We see RE in parallel with R pi. So this is R pi, RE. And this node here is because Vi equals 0. Okay. So now we can go and write out the expression for A equivalent, which is again VO over Vi under these conditions, right, from this picture, where the input network was done, created by nulling the output signal, and the output network was done nulling the input signal. This is sort of what's convenient about this method, that you only need to figure out what's happening where the input gets nulled and the output gets nulled. You don't sort of have to go in the guts of the feedback and try to null the sources and try to see where things go. Okay, so in this case, what we're getting is that VBE is R pi over R pi plus RE. That's this first voltage divider. And then times minus GM times RC. So in this case, I can just do it like this. So minus GM is our K, or GM is our K, right? So that's the middle term. And then RC is the termination network at the output. Right? Okay, so we have return ratio. We have A0 and A equivalent. And now we can write the A closed loop as A equivalent over 1 plus return ratio. Okay, so, and that will be then just R pi over RE plus R pi times minus GM RC. That was our A equivalent. And then 1 plus GM R pi RE over R pi plus RE. This is the return ratio, 1 plus return ratio. And that is equal to minus beta 0 RC, because GM R pi are beta 0, over R pi plus RE times 1 plus beta 0. Okay. Okay. Let's do another example that's a little bit different topology. So we're going to do common emitter feedback. Going to have VCC here, RC, and then a bipolar transistor like this. We're going to close the feedback loop from gate to drain. And then here have actually a current source. Okay, again, A closed loop will be A equivalent over 1 plus RR plus A0 over 1 plus RR. And the small signal model, I in, R pi. Then we have RF here. GMVBE. I can add here R naught, doesn't really matter, it doesn't change anything. So we'll just call it RC prime. Or we can just say approximately RC. Okay, so V out will be here. Okay, so in this case, when we try to do return, so under 1, we will have to figure out what return ratio is. When we are disabling the input, the current source becomes an open, right? Because it's an independent source. So when we look at this, we're going to say, okay, well, the feedback goes from this VO through RF, and then comes to this point over here, gets translated into VB. So for me to cut the feedback, I'll sort of do it here. Okay? And in that case, my current source becomes an open. I'm adding VTest right where the R pi is. So this is VBE. And then what the VTest sees, it's R pi, so I'm going to terminate with R pi, and this is going to be VR. Over here, I have nothing because that's where the current source was, and then I have RF, and then on this side, I have GM VBE, RC, and then the RF connects. So in this case, we'll derive what VR is. We have minus GM times VBE. That's the source here. But VBE is VTest. So it will be minus GM VTest. So that's the current we're pulling from here. And then we have that current going into the parallel connection of RC and RF plus R pi. And then, or we can just basically maybe do a little bit better job with that, saying that this current is going and getting a resistive divider or current divider between these two. So it will be really just RC over RC plus RF plus R pi. And then times R pi, because that same current will just flow through R pi and generate VR. So we're taking a little bit of a shortcut here. So then the return ratio is minus VR over VT, and that is going to be just GM times R pi times RC over RC plus RF plus R pi. So under 2, let's do the A0. So in A0, again, we have to eliminate the, or let me just circle it here. We have to eliminate the K, or in this case, it's GM again. It's the coefficient or the gain of the controlled source. Right? So we null the controlled source, and we're only looking for the feed-forward path from the input to the output. So again, A0 is VO. Well, in this case, it will be versus I in. So the output voltage versus input current for GM equals 0. So in order to do that, we can draw the diagram. So we have I in, and then over here, we don't have the GM VBE, but here we have R pi, and then RF. And then on this side, we have RC, and then we're looking for V out. So in this case, this is equal to, again, RC times the current after the divider. So it will be R pi over R pi plus RF plus RC. Okay, makes sense so far? Good. So the remaining thing we need to do is find the A equivalent. Okay? Okay, for that, again, we apply the trick. We need to null the output, see what the input termination network looks like, have our gain, and then null the input and see what the output loading network is. Right? So we have I in, and then if we go back to the previous drawing, over here, if we null the output, what we see from the input is just RF. Right, because we've nulled this node over here. Okay. So we're going to have our normal R pi, but then we're going to have RF in addition, because here, this is the output that was grounded. Right? And then this is our VBE. And then we have GM VBE. We have RC. And now we have to figure out what is the loading that's presented by the feedback. And if we go back, now we have to see what happens when there's no input signal. Right? So in this case, when this is 0, then this branch is just gone because it's a current source. Right? So we're really seeing RF in series with R pi. I'm going to do it like this. And this open is because I in equals 0. Right. So now I can write A equivalent is V out over I in this scenario above. And so that would be, for the first one, would be R pi in parallel with RF times GM. So this is the first term. This is the second term, or I would say minus GM, times, and then again we have the resistive divider, RC over, or in this case actually we're just going to do the parallel. So RC in parallel with RF plus R pi. So this is again the third term. And this is normally the load, but in this case, this load is kind of in parallel with feedback loading. Right. This piece over here. Okay. And then, of course, the closed loop is going to be A equivalent over 1 plus RR plus A0 over 1 plus RR. And I'll let you sort of go through it if you want. OK. So I think it will be useful now that we've kind of gone through a few of these examples to revisit a little bit this recipe and also see what an alternative is. When I did the original derivation, I sort of skipped over that alternative simply to get you to what I think is the most or the simplest way of doing it, right? Which is nulling the inputs, nulling the outputs. And the reason is it's kind of like those things you know where they are in every circuit, the input and the output. The rest you have to sort of think about where to find it. But I'll show you an alternative, and it's also in the book. Actually, in the book it's shown first. So you can judge for yourself on a few examples which one's easier. But just so you have a big picture. So what we're really looking at when we do the closed loop gain is the ratio of the output signal to the input signal. And just kind of as a refresher from last week, we have the input signal goes through this gain B1. A summation node. We have our controlled source, which is a transistor or a set of stages, doesn't matter. That's where our amplifier is. And then we have the output network, another summation node, and then S out. And we can feed directly where this D represents some feed-forward effect that the feedback network creates. And then the feedback itself is really happening here in H. All these boxes, the way they're drawn, are unilateral. For example, H here just represents the flow this way. So if I'm trying to model the real feedback, that actually is, for example, just a resistor, so it's bilateral, then that bilateral effect or feed-forward effect will be mapped into D. Okay? So this was our general kind of example or model. And then we said that, after you sort of relate the SI and SJ with these blocks and input and output signals, what you get is that the loop gain looks something like this. It's B1 K B2 over 1 plus KH, and then you add D, which is kind of an independent feed-forward path. Now we're going to do a little bit of massaging to get this into different forms to interpret. I'm going to say that I'll just label G to be B1 K B2. Notice that before we do any massaging, that our return ratio is actually KH. We can just go exactly by the definition of the return ratio, right? We could cut the loop here, insert VT, look at VR. This will go through H. I would null the input node. So signal from S in will be 0. So the only thing I'm going to get is VT times H times K. And it's going to map to here. So return ratio is KH. So our closed loop, in that case, will be G over 1 plus return ratio plus D. So G, we can say this is the gain when H equals 0 and when D equals 0. So when there is no feedback and feed-forward path is also kind of eliminated. That's kind of what the physical meaning of this G. So now we can do a little bit of massaging similar to a few lectures ago. We can move this D in here. And then separate out these effects. Now we can write the closed loop gain as G over RR plus D times RR over 1 plus RR, and then plus D over 1 plus RR. We called this piece over here A0, and we called this whole thing A equivalent. Okay? That's it. However, this form that I just wrote it in separates explicitly return ratio and this piece here in the bracket. Okay? So what we're going to instead call this is we're going to call just this piece over here A infinity. And then we're going to leave RR here. So our A closed loop will be A infinity times RR over 1 plus RR plus A0 over 1 plus RR, where A infinity is G over RR plus D. A infinity is sort of the meaning is it's the gain, so closed loop gain, with when RR goes to infinity. So if the return ratio goes to infinity in the loop, then sort of the loop has ideal feedback, right? So you have an ideal, for example, you have an ideal op-amp in the loop. So this also happens with K goes to infinity, means that RR goes to infinity. Right. A is essentially 1 over F. Okay. So that sort of relates back to what we talked about sort of in the most germane topologies where you sort of know exactly what F is. So even if you don't know exactly what F is in terms of resistors that you put in there, when you set K or the dependent source to be going to infinity, you're forcing RR to go to infinity simply because RR is KH. Okay. And then under those circumstances, the closed loop gain really becomes just A infinity or 1 over F. So if RR goes to infinity, this factor goes to 0. This factor goes to 1, and then you're just left with A infinity. That's why it's called A infinity here. So that's the closed loop gain when the K goes to infinity or RR goes to infinity. And that, by the way, is also the recipe how you're going to find it. In the loop, you're going to set K equals to infinity and then solve the input and output relationship. Hopefully things get simplified, because if the gain of the amplifier is infinity, that means that for finite output voltage, the input is 0. So it pretty much behaves like your ideal op-amp, right? And then you can go simplify the circuit, calculate that gain, and hopefully you'll be able to do it. Okay, I'm saying hopefully because procedure is sometimes trivial. So it's a lot easier than A equivalent, but sometimes you sort of have to chase things around the loop and really figure out how to do it. So if you have A infinity, then you're done. Then no need for A equivalent, right? Because A equivalent is really A infinity times return ratio. And we always first find the return ratio. Okay. So in summary, there's sort of, well, let me draw just the diagram, and then I'll kind of give you the back of the envelope. What this really boils down, we have S in, we have the summation node, we have our A equivalent, or in this case, so this is A infinity times return ratio. And we have another summation node, and this is our S out. And then from here, we're feeding back 1 over A infinity. Remember, A infinity was 1 over F, ideally, right? So this is 1 over F, which is F. Right. And then we have this extra effect that we kind of didn't have in our normal model. Remember, I'm trying to make this equivalent to this model. Right? So this model obviously doesn't capture D, this model over here. But if we say D is not that important, then you have some resemblance between A equivalent and 1 over F. Okay, so let's do an example, hopefully, because this is now a familiar one, it'll go quickly. Okay. So we're going to do the same exact thing that we did just a moment ago with A equivalent, right? So now we're just looking to find A infinity. Because we have the return ratio, we have A0. So this is the only missing piece, if we don't want to do the A equivalent. So for this, we're going to set K to infinity, which means that GM goes to infinity. The practical implication of GM going to infinity, because V0 is finite, this means that the output current is finite, which means that VBE has to be equal to 0. Because I multiply, my output is GM VBE, and that goes into RC, and then feeds back through RF into R pi, and then IN. Okay. So if I want to have a finite current here, and my GM goes to infinity, then VB has to go to 0. 0 times infinity will give me some, just like in normal ideal op-amps, right? So if that's true, then VBE is 0, so there's no current flowing into R pi, meaning that all the input current is flowing through the resistor. That also means, just like in op-amps, that since VB is 0, this voltage is 0. Right? So what is then V out? This voltage is 0, and I'm pushing current I in through RF. What is the output voltage? Is it going to matter what RC is? I'm just pushing the known current through RF, starting from 0, and then I immediately touch V out. So V out is I in RF. Yeah. So it's minus I in times RF, right? And then my A infinity is just VO over I in, which is minus RF. Well, that's to be expected. If you looked sort of back into the ideal op-amp type stuff, your 1 over F would just be determined by the feedback resistor, right? Because your input is kind of grounded. So all the input current flows through. OK. Now you can go and sort of, we have the RR, which is same as before. We have A0, which is same as before. And then we're going to do A closed loop will be A infinity times RR over 1 plus RR plus A0 over 1 plus RR. OK, so when we plug the expressions into this, just in terms of, let's say, checking the A infinity times RR, we're going to get minus RF, which is this, times, and then RR from previous pages was GM R pi in parallel with RC over RC plus R pi plus RF. Contrast, our A equivalent was minus R pi in parallel with RF times GM times RC in parallel with R pi plus RF. So if we want to sort of massage this a little bit so it's we show it's exactly the same as the previous one. So you can write it like in the developed form. And then here we're going to have RC times R pi plus RF over RC plus R pi plus RF. So these two will go away. And then if you look at the previous example, it's basically exactly that thing, right? Because we have RF separated out, the same thing here and then here. OK. So in summary, here's the analysis approach. One, we have to find RR. The process for that is we cut the loop, insert VT, terminate with what VT sees. Calculate VR, right? That's it. Two is we have to find A0. And finding A0 means set K to 0. Whatever K is, right? K could be GM, could be A, whatever we have in our loop that is sort of a coefficient that controls the dependent source. So this means Kiel dependent source. And then calculate or let's just say S out over S in for K equals 0. Number 3, now we have a choice. So these first two we do regardless, okay? Now under 3, we have a choice. Under A, we're going to find A equivalent. Under B, we can decide to instead find A infinity. Okay. The way we find A equivalent, we set signal S in to 0, calculate output load, and then also setting S out equals 0 and calculate input load. For A infinity, we just set RR to infinity by setting K to infinity. And then our A infinity is S out over S in for K goes to infinity. So once we're done with this, in this case, in 3A, under 4, we can calculate A closed loop as A equivalent over 1 plus RR plus A0, 1 plus RR. Whereas in B, we can calculate a closed loop as A infinity times RR over 1 plus RR plus A0 over 1 plus RR. Okay, so this should be sort of the general recipe, right? And what we're going to do, as you saw in all the previous examples, is basically the same which method you use. But sometimes it's easier to use A equivalent. Sometimes you can immediately see what A infinity is, and then you don't have to calculate these input-output loading networks and what A equivalent is. So it just really depends on the topology of the circuit. And we're going to do a few more topologies in the next lecture, a little bit more complicated ones. Alberto is going to do some in the discussion sessions. So hopefully, by practicing enough, you'll kind of get a hang of it. I'll also show you, we're going to do the impedances of closed loop amplifiers, also by using the return ratio methods. And then I'll also show you, just for kind of your information, the two-port network analysis. But you'll pretty quickly see how involved it is, and you'll hopefully say, no, we don't want to go down that road. But it goes sort of along the lines of what I started showing you. Shunt, series, series, et cetera. And then for each one of these types, you actually have to figure out what's the equivalent amplifier path, what's the equivalent feedback path, and do it. So it gets out of hand pretty quickly there. So that's why I'm showing you these return ratio methods, because in practice, they're actually a lot easier to deal with. Okay, we'll stop here. 5 minutes short so that we don't go into big examples at the end.